Okay, can you hear me?
Yeah?
The next talk is by Remy Willems from AWS on how to reduce brittleness in Dafny programs.
All right. Hello, everyone. My name is Remy. I'll be presenting this talk about helping users reduce brittleness. It's joint work between myself, Matthias Schlaipfer, and Olivier Bouissou. First, I'll show you an example of brittleness. Then I'll show you a way to measure brittleness. Then I'll go over 3 features that have been added to Dafny that help Dafny users reduce brittleness in their programs. And then I'll conclude. So first, let me show you what brittleness is. So I've taken a Dafny proof shown on the left side, and it's just showing part of a proof, so lots of the statements have been left out. And I've made a small modification to this proof. So I've taken the statement on line 6, and I've moved it up a few lines, but this statement does not relate to the statements that I moved it over. So semantically, there's no change in the program, and we don't expect any change in verification. But now if we look at verification time, then we see that the program on the left consistently verifies in 11 seconds, while the one on the right consistently verifies in 16. So there is a change in verification. And now this change might not matter so much to the user, but when it comes to brittleness, the effect can be much bigger. So for example, a harmless change can cause a proof to suddenly verify 10 times as slow or 100 times as slow, or Dafny might no longer be able to verify the proof at all. And that's a big problem for users, obviously. So brittleness is when a small change to a Dafny program, one that seems harmless, can cause a big effect in the verification output. You can see that I've also noted these resources numbers in the bottom. So besides verification time, Dafny also emits resources used as a metric when you verify a proof. And this is similar to verification time in the sense that it more or less scales linearly with verification time. But what's nice about it is that it's deterministic. So if you verify the proof again, the verification count will be the same. And this property is so nice that in the following slides, I only look at resource count and not verification time. So in the previous slide, I showed you an example of brittleness, but I also want to show you how do we figure out how brittle a particular proof is. And we can do that by making not just one mutation to a proof, but by making many mutations, similar to the one I made in the previous slide. So here I've taken 2 proofs, one show white proof that's brittle and another index of proof that's not brittle, and I've made 1,000 mutations to both. And in the graph on the left, you can see how for each mutation, the resource count changes a lot for the show white proof. And you can see the resource counts they vary a lot. And on the right, you see the striped bar that shows timeout and also failures, so situations where Dafny was no longer able to verify the proof at all. But for index of, the not brittle proof, you can see that for all the 1,000 mutations, the resource count stays tightly centered around the mean. And if we want to summarize the graph on the left, we can compute the relative standard deviation of resource count. And then we see that for show white, it's 1.4, while for index of, it's much less. So on the previous slide, I showed you a way to measure brittleness, but that's a time-intensive method because it means having to verify a particular proof for many mutations. And if you have a large code base and you want to quickly iterate on a particular proof, then you might not want to compute all these mutations all the time. So it's great to have a faster way to guess or to know that a particular proof is brittle. And we've found that it seems like there's a positive correlation between brittleness and resource count. It's hard to prove this correlation because in real-world programs there are few brittle proofs because Dafny users tend to remove brittle proofs from their code base. But here I've taken some real-world libraries and from there it seems like there's that positive correlation. So if you look at the graph on the left, you can see that as resource count goes up, relative standard deviation goes up as well. And if you look at the graph on the right, you can see that as resource count goes up, the number of times a particular proof has mutations that contain failures goes up as well. So in the following slides, I will look at Dafny features that help users reduce brittleness, but the way in which I'll measure it is to see to what extent those features reduce resource count, in the assumption that that also helps reduce brittleness. Okay, so let's look at some Dafny features that help reduce brittleness. First, I'll go over assertion isolation. This is a feature that's been in Dafny for a while, but we've recently extended it with a few parts that I'll show a bit later. Here you see a proof max of concat, and there's an explicit assertion on line 9 with this by isolate clause. And what that clause does is it tells Dafny not to prove the max of concat lemma all at once, but to do it in parts. Each part we call an assertion batch because it contains one or multiple assertions. And in this case, there will be two batches, one that asserts just the explicit assertion on line 9, and the other that will assert all the other assertions in this program. Now you might say, what other assertions? But there are many implicit assertions in this program. So let's look at what the batches look like. So here's the one that contains just the explicit assertion that we isolated. You can see there's an assumption at the start that comes from the requires clause, and there's two other assumptions. These come from the requires clauses of the preconditions of the subrange expressions that we have in the condition on line 5. And if this had been one big batch, those assumptions on line 3 and 4 would have to be asserted as well, but now we've moved those assertions to a different batch. So in this batch, they're just assumptions. And then if you look at the second batch, then we can see that the explicit assertion that we isolated, here it's on line 5, has now turned into assumption. So these two assertion batches by themselves are simpler than the single assertion batch we had before, and that means their resource count is also lower and that they're likely to be less brittle. We can also isolate other statements than just explicit assertions, as you see here, and this allows us to isolate any explicit or implicit assertion that occurs in the Dafny program. And if you want to isolate all the assertions in a particular proof and you don't want to type this by isolate so often, you can also use different syntax to isolate everything at once. Now, the syntax that I'm showing here is not the syntax that Dafny is currently using, but this was easier to read for the slide, so I've used this. But you can find the current syntax in the documentation. So let's look at what isolating assertions does to resource count. You can see in the table on the left, that on the graph, in the graph on the left, that as we isolate more, the maximum resource count of any of the assertion batches goes down, but in the table on the right, we can see that the more we isolate, the total resource count also goes up. And for that reason, Dafny does not isolate assertions by default, because that would slow down the verification of large projects. So we leave it up to the user to decide when a particular proof seems brittle, and then for that proof to decide to isolate maybe particular problematic assertions or all assertions, so that the project as a whole doesn't change much in its total verification time, but there are no particularly brittle proofs. Let's go back to the Schlaipfer proof that I showed before, the brittle Schlaipfer proof, and see what happens if we isolate it. Now you can see it in this graph. Once we isolate all the assertions in the Schlaipfer proof, suddenly it's not brittle anymore. So now the resource count stays tightly clustered around the mean. And then a recent feature for assertion isolation that we added is path isolation. So instead of isolating a single assertion, we can also isolate a pair of paths and assertions. So here we're saying for this this call that happens on line 9, it has preconditions that need to be asserted, and we want to isolate each pair of a path that leads to this call and the preconditions of that call. And in that way, we get more isolations, and those individual isolations are easier to prove. This is a new feature, so I don't have real-world data on it yet. Okay, now let's move to function hiding. One problem that we've noticed is that when Dafny' tries to verify a proof, the more information that is sent to the solver, the more difficult it is for the solver to verify the proof, and the higher the resource count becomes, and the more brittle the verification becomes. And the one way in which a lot of information gets sent to the solver is through the definitions of functions. So what Dafny' tries to do by default is to figure out which function definitions will for sure not be needed to verify a particular proof, and then not send those to the solver. But sometimes Dafny' doesn't know whether a particular function definition is needed, and then it has to send it over in case it is needed. And for these cases, we enable the user to tell Dafny', no, this function isn't needed for the proof. So the way to tell Dafny' that is using hide and reveal clauses. And a way to use those is using hide star. So suppose you have a method that's brittle, suppose this method foo is brittle, then we can start by saying hide star, and that means that after that point on, all functions are hidden, all function bodies are hidden. So we won't be able to prove much, and if we try to verify this assertion on line 5, assert p of 0, then that fails. But after we reveal p, like we do on line 7, then we'll be able to once again verify assert p of 1. And we can see what effect this has on real-world data. So this is data taken from an unreleased AWS project, and they've used hide and reveal statements on some of their proofs. So many they have not used it at all, but some of their proofs that were problematic, there they've used this feature. And you can see that there's a big reduction in resource count in general, and for them this has been really effective. Okay, now let's go to opaque blocks. So first I'll motivate opaque blocks, and one thing we see is that Dafny' method sizes vary greatly, so they can be 200 lines or even longer. And the problem with that is that the resource count of verifying a method increases super linearly with method length. There are many reasons for that, but one reason is that every time a Dafny' program mutates the heap, this creates a new heap layer, and that makes it more difficult to read data from the heap afterwards. And well, a way to deal with the problem of large methods is to make them smaller, which a Dafny' programmer can do by extracting smaller methods from a larger method. But the problem is that this can introduce a lot of boilerplate in terms of method signatures and call arguments. And we wanted to lower the bar for doing this extraction. So we've added a new feature called opaque blocks that looks like this. So the way to create an opaque block is to add the keyword opaque in front of a block. And what that does is that everything that happens inside of the block becomes invisible to the context outside of the block. So here on line 9, we're assigning the value 1 to the variable r, but on line 11, we won't be able to assert that r equals 1 because that assignment was invisible to this point. So then we still need a way to know something about what happened in the block, usually at least. And that's possible through ensures clauses on the block. So on line 5, you see this ensures clause, and that allows us to prove the assertion on line 12 that has the same condition, r is bigger than 0. Opaque blocks also have modifies clauses. So this one has an empty modifies clause, which means the heap is not modified at all by the block. So we knew before the block c.a equaled 1 because of the requires clause, and that means that after the block that's still the case, which allows us to prove the assertion on line 14. And what's nice about opaque blocks is that, well, in this case, because the modifies clause is empty, there's no extra heap layer introduced, even though we are modifying the heap inside the block, but no part of the existing heap was modified. We're just creating, we're just allocating a new object. So that can happen sort of opaquely. And then also, if we were modifying parts of the original heap, then if we would do multiple modifications, that would still show up only as a single extra heap layer to the context outside of the block, which is also better for performance. And to better understand the effect of opaque blocks, we can look at assertion batches like we did before. So here's the assertion batch for the previous program if we had not used opaque blocks. And you can see there's two heap variables, heap 1 and heap 2. And these are tied together using a quantifier on line 5. And that means that if we want to prove something that involves both heaps, like the assertion on line 13, R2 is bigger than 1, then we need to instantiate this quantifier, which can be an expensive operation. So here's the assertion batch if we do use the opaque block, and you can see it's much simpler. There's only a single heap variable and there's no quantifier, so it's much cheaper to prove the assertions here. Opaque blocks are a new feature for Dafny, and I don't have real-world data on them yet. We have applied them to some real-world proofs with great results, but here I'm showing data just from a toy method that I made myself. It's a very boring method. It repeats the same code 200 times, and it creates an object, sets a field for it, and then passes it to a method call. And I've measured how the resource count of verifying a single assertion in this method goes up the further down in the method that assertion is located. And you can see that the further down we go in the method, the more the resource count increases exponentially if we're not using opaque blocks. But when we do use opaque blocks, then the resource count used by the assertion stays, doesn't stay the same, but stays much more the same as the method grows longer. So for this toy program, opaque blocks make an absolutely huge difference. So to conclude, it seems that brittleness is correlated with resource count, and we can add language features to Dafny to enable users to reduce brittleness, in particular assertion isolation, function body hiding, and opaque blocks. And then for future work, we plan to enrich or extend the work that we've done with hide statements. So we want to make it easier for users to know what hide and reveal statements to add to their program, which we'll do using IDE code actions. We also want to enable users to hide not just their own function definitions, but also definitions from the Dafny prelude. And we want to enable hiding subset types and insurance clauses. And then lastly, so this is something that doesn't require any user involvement, but we want to improve the efficiency of the Dafny to SMT encoding so that the resource count is reduced in all cases. Okay, that was it. Are there any questions?
Hi.
Not oh. Go ahead.
Can you hear?
Yes, I can hear you.
Thanks. What does the resource count actually measure, just to get an idea of that?
Sure. Yeah, it's a metric that's emitted by the SMT solver, and it's the SMT solver is implemented in a way so that the resource count attempts to scale linearly with verification time. So the intention of that metric is that if verification time doubles, resource count doubles as well. Now, it's impossible to make that correlation be exactly linear, but there is a strong correlation, and because it is a deterministic metric, it's nice to use because then you can get consistent measurements. And for example, you can say if the resource count for verifying this particular proof goes above some threshold, then I will fail. And if you would do that with verification time, then you might get unstable behavior, which you don't want.
Thank you.
Hi, this is Peter Müller from ETH. Thanks for a very nice talk. I just wanted to mention, because you said you had no real data yet for the opaque blocks. So we have basically the exact same statement in our Gobra verifier. We call it outline statement. And we used it quite heavily in a very large verification project, and it made a huge difference for us. So there were many large methods that we couldn't verify without this feature, but with the feature, it was quite doable. So our real-world experience is that this feature is actually extremely helpful.
Oh, that's really good to hear. Well, yeah, that sounds great. I will look at that feature, see how it compares, and also see if you've published some data on it.
One last question. Could you say again how the heap layer is modified by an opaque block? Is it
always create its own new heap layer, or essentially does it? What is its relationship to the existing context in the program in a method?
So normally, if you have an operation in Dafny program that modifies the heap, a new heap variable is created. And for an opaque block that has a non-empty modifies clause, that happens as well. But then from the outside, it seems as if the entire opaque block is a single operation that modifies the heap. But inside the opaque block, you might modify the heap 100 times. So if you would not have the opaque block, you would get 100 heap variables. So a very deeply nested heap. But with the opaque block, you only get one nesting. I hope that answers your question. I'm not sure if I understood it correctly.
All right, let's thank the speaker again.
All right. Thanks everyone for listening. You.